Okay, so this is the 14th class of problem solving. I have almost recovered from my cold, so I'm beginning to get my sense of balance back. I should have my enthusiasm by next week. And so what I want to do today is to continue the monovariants. And so we'll start off with an easier problem, and then we will return to the card sorting. So this is the tournament problem. And there's lots of different tournament types of problems you can give. This is a very famous one. You have n teams. Win or go home. So out with one loss. So as soon as you lose a game, there's no second chances. You're done. You're gone. Okay? You always play games of two. Two teams play together. Okay? If you have an even number of teams, you just divide everybody up randomly into pairs of two, and they play. If you have an odd number, then one team randomly gets a bye. So if even, randomly match in pairs. If odd, one lucky team doesn't play. Okay? So the question is, how many games until we get a champion? Okay? So thoughts about how you would attack this problem? Yes?
Well, you can only let one team go in one game, right?
Right. So when two teams play, one team wins, one team loses. There's no ties.
So in order for n-1 teams to go home, we must have n-1.
Good. So each team that goes home is a result of a loss. So it's n-1. Right? So this is a fairly straightforward one as soon as you look at it the right way, that for each team, it plays a game. And I'll count the game with the loser. So for a team that keeps winning, I'm not counting it as having played any games yet, but I don't have to give credit to both teams for playing that game. I just need to give credit to one team for playing the game. And every game results in another team losing and decreasing. So you can see what the monovariant would be. Maybe number of losses. And it'll keep going until you get to n-1. Or number of teams remaining, and that goes down from n all the way down to 1. If you hadn't seen that, if you hadn't seen the idea of just looking at every loss, every team has to lose one game except for the ultimate champ, how would you have attacked this problem if you didn't see that? So if you hadn't seen that, how could we try to get an idea of what the answer is? What should we always do when we see a problem with, a general n? Small cases. Right. So if you start off with n equals 1, okay, there's only one team, they're the champion. If there are two teams, there's one game. If there are three teams, two teams randomly play, somebody loses, and then that team plays the person who had the bye, and you see that there's two games. So you begin to see, it looks like it could be n-1. And so if you look at small cases, this could be suggestive of the pattern. One situation where you might have seen something similar to this is in graph theory. If you're trying to count things with vertices and edges, how many of you have seen Euler's formula? You're relating the number of vertices, edges, and faces. Sometimes you have to be careful that you're double counting an edge, because you can count the edge both when it's leaving a vertex and when it's arriving. So sometimes you want to just divide by 2. So you just want to think about how you want to count objects. Okay, so that finishes the quick warm-up. Everybody hopefully is now awake. Now we can go back to the fun card problem. One of the nice things about recording my lectures is I can go back and see how I taught this 3 years ago. And so Kayla was a little bit younger back then, and we liked to play Go Fish. I am happy that she likes to play better games now. So I now have the cards 1, 2, 3, all the way up to 10. So the way the card game works is we shuffle the cards, and then we put the cards down. Oh, this one. I don't like that. So here it's 8, 2, 1, 6, 4, 10, 7, 5, 3, and 9. And that will probably not be visible to anybody watching at home. So, all right, maybe 8, 2, 1, 6, 4, 10, 7, 5, 3, 9. So if first card is not 1, but K, reverse first K cards. Do until we cycle or hit 1. Well, of course, if we hit 1, then we've also cycled. So here's the first question. Will we always get into a cycle? And again, if the first card is 1, that must count as a cycle because we just keep flipping 1, 1, 1, 1, 1. So why must we eventually get into a cycle? Yes?
There's a limited number of orders.
Yeah, there's only finitely many combinations. If we have n cards, we have n factorial orderings, must be in a cycle in, at most, and this is ridiculously high, n factorial plus 1 moves. So we know we'll at least eventually cycle. So in this case, I would flip 8. So I'd have to go all the way to 5. So 1, 2, 3, 4, 5, 6, 7, 8. We'd have 5, 7, 10, 4, 6, 1, 2, 8. And so I thought it might be worth just gathering some data. So here's our first round. Now we have 5, 7, 10, 4, 6, 1, 2, 8, 3, 9. All right, so now I got to flip the first 5 cards. 1, 2, 3, 4, 5. And again, I wanted to do something large like 10 because that would give me hopefully far enough down so I'm not going to get small cases and be maybe misled. So now I've got 6, 4, 10. Oh, that's interesting. 7, 5, and then 1, 2, 8, 3, 9. All right, so now I've got to flip 6. 1, 2, 3, 4, 5, 6. Okay, well, that's looking pretty good because I see the 1 coming to the front. Okay, and so now we will have 1, 5, 7, 10, 4, 6, 2, 8, 3, 9. And now we'll just keep always having 1 in the front. So the question is, how do we want to attack this? Is this a monovariant problem, or did I just happen to give this to you in the monovariant section? So it could be possible to do it with a monovariant, but it might be better to do it with something other than a monovariant. What do people think? How should we attack this? Any partial results? Anything you notice?
I mean, the number on the right, the numbers that were on the right side set, like kind of grew. It was 9, 3,
Ah.
5, and then it was 9, 3, 8, 2, and then it remained 9, 3.
So that's really interesting.
But it didn't completely because it was 9, 3, 8,
Wait a minute, but it's still growing, right?
I meant that like there was a group of numbers on the right hand side.
Okay, so there's a group of numbers on the right-hand side, yes.
There's 9, 3.
Mm-hmm.
There's 9, 3, 8, 2, 1. And then there's 9, 3, 8, 2, 1. And then it went back to 9, 3, 8, 2.
Oh, okay, because this would be 1, 6, and this is 1, 5.
Yeah.
Right. So it's not strictly growing.
Yeah.
So then what if we look at smaller sections? We just look at the first 2 digits here versus the first 2 digits here. They're at least as good. Then maybe the first 3 here versus the first 3 here. The first 4 versus the first 4. Maybe a more restricted study.
That might work.
Or do you think that there's a way I could possibly arrange it so that...
I think there's a way you could possibly arrange it. I think if you stuck at 10 where the 1 originally was, right, in 4 turns you would have a 10 at the start, and then you'd be rearranging everything.
Right.
So never mind.
But again, it's good to try to figure out what the monovariant could be if there is something. Or maybe the monovariant only comes into play if we don't hit the 1. So, to me, it's not at all clear how we should be viewing this. We'd love to say that there's some kind of quantity associated, in terms of maybe looking at where the 10 is, but we see the 10 is bouncing around. We see the 1 is bouncing around. You're trying to look at what's going on from the right. Maybe like a lexicographical, maybe an alphabetical ordering that's going from highest to lowest as we go like this, and the numbers are only increasing. But, no, we do see it went down, then went back up. And so, but I don't know, so...
I think what you might be able to say is once you get a 10 on the right, it's not going away.
So once we get a 10 on the right, we're done.
And once you get a 10, 9, that's not going away. And once you get a 10, 9, 8, that's not going away.
So what's that suggesting?
Well,
What approach?
Well, if there's, I think what we could say is, we have, it's going to go into a cycle.
Right.
So we're going to hit, once we, let's say that we,
So rather than give me the solution, I'm saying, what kind of attack are you suggesting now? If you're saying once we get a 10, then once we get a 10, 9. What method of proof? Yeah, this is suggesting this is an induction approach. So maybe we should hold off on trying to do this by monovariants and go back and say, can we do this by induction? Because the whole point is, if we ever have a 10 at the far right, we've now reduced to a lower case, which we assume we know. What if we ever have a 10 at the far left? Yeah, then the next turn, the 10 goes to the far right, and we're done. So we could try this maybe by induction. So let's do a proof by induction. Assume n is smallest such that there exists a configuration that doesn't cycle to 1 at start. So if it fails, there has to be an n that's the first failure. There might be many different configurations that fail. Let's choose one of them. So now if we have something like this, we know we have to cycle, because we only have finitely many states. And we know the 10 can never be in the first or the last spot. Okay? So we know we cycle, and n is never in spot 1 or n. So for definiteness, I'll take the cards. If we're in a cycle, does it matter which one I say is the first element of the cycle? No, because they just cycle and they'll keep going through all of them. So let's say this is my cycle. 3, 7, 1, 5, 4, 10, 6, 2, 8, 9. Okay. 3, 7, 1, 5, 4, 10, 6, 2, 8, 9. I'm going to draw a really big line here, and I'll draw a really big line here. And we know our n, which we're calling 10, only moves in through here as we cycle. We're now one step away from solving the problem.
Could you replace the numbers with one less? Or with something?
Well, I mean, if I replace 1 with 1 less, that'd be 0. If I replace 3 less with 2, and then that would affect how I move things. So you're right that we want to somehow shift it down to something we've already studied. We can't quite do that by just replacing everything with a number that's 1 less. But it's close. We do want to do a replacement. Which card do you think we want to replace?
Could we just get rid of the 9? Because we're never going to get to the 9 ever.
Okay, so this 9, we never reach it. It doesn't matter what number this is. Which other card do we know doesn't matter? The 10. Right? As the 10 moves around,
As the 10 moves around, we'll never reach it. So the 10 can very well just be 9.
so did I switch them? No idea. Does it matter if I switch them? If the assumption is correct that 10 never reached the front and 10 never reached the back, I can't tell the difference between switching those two cards. Let's see if I switch them. I did switch them. Perfectly lucky, but so I switched them. Yay! By induction, we're now done. Because now there's n minus 1 cards here. And we know that big N was the smallest n such that it does not end up with 1 in the starting position.
Is this an induction? Or
Yeah, I mean, this is an induction proof.
is it a contradiction proof?
Yeah, I mean, you prove the induction by or what we're really doing here, yeah, I guess it's a contradiction because we assume that it cycles, but 1 and n never go to the first or the last spot. And then if that's true, we can then replace the n card with whatever was in the last spot. And we'll never see any difference as we cycle. And then we would now have n minus 1 cards cycling, but by the inductive assumption, n minus 1 card cycling will eventually have 1 come first. And so this finishes the proof. So we replace n with what was at the end. And that will give us the proof. Okay. Any other thoughts on this? So there are ways to try to attack this with monovariants. And so someone in the class had sent a suggestion of how to look at this with some kind of ordering. And trying to look, as we're going through things, I think it was which cards may be in fixed positions. And so it may be possible to do this with a monovariant. But to me, it seems like it is a much better problem to do by induction. And this is the real challenge in problem solving. As we develop more and more material, it becomes harder and harder to figure out what we want to use. Okay. Any questions on this? All right, so I'm going to end with a really challenging monovariant problem. What do you think the hardest part of monovariant problems are? Yeah, it's just like when you're doing a pigeonhole problem, usually the pigeons, it's pretty clear what the pigeons are. The boxes, that can be a real challenge. I think this problem is due to John Conway, which will give you an idea that it's going to be challenging and there will be a beautiful, elegant solution. So I heard it called Conway's famous checker problem. Okay, so do you remember how early in the semester we had some chessboard problems and we had like 5x5 boards and stuff like that because of budget constraints? This is being done at Princeton. They have an incredibly large endowment which they're willing to use for this problem. It's nice being a grad student there. The budget restrictions are gone. We will be working on the infinite lattice. So here is y equals 0. Here's y equals 1, y equals 2, y equals 3, y equals 4, and we'll call this line over here y equals 5. We'll go down and we'll have y equals negative 1, y equals negative 2, y equals negative 3, and so on. And I believe we start at y equals 0. Yes. And so, just for definiteness, this is the line x equals 0. And what we're going to do is at every lattice point whose y-coordinate is 0 or lower, we're going to put a checker. So this does mean, yes, we have placed down infinitely many checkers. But this is why we used smaller chessboards early in the semester. We saved our budget for this problem. Has everyone here played checkers? Okay. One of my good friends in high school was from the Soviet Union, and every time we played, she seemed to add a different rule. Oh, no, in my country we also have this rule. Okay. So we'll play a very simplified American version. So the way checkers works is you can jump a piece if there is an open square immediately above it. You can't jump diagonally, and you have to have a piece to land onto. You can either jump vertically up, vertically down, horizontally right, horizontally left. So what is the only possible opening move? Jump up. And without loss of generality, what is that opening move? Yeah, you might as well have this piece move up 1 at x equals 0. Jumps this piece and lands here. So what you've just shown is it is possible to promote a checker to the line y equals 1. Is it possible to promote a checker to the line y equals 2? Okay, how could we do that?
Half the one on like x equals 1. Yeah.
Okay.
Or the one on y equals negative 1 and x equals 1.
Okay, y equals negative 1 and x equals 1. Okay, that's one over here.
And jump it up to y equals 1.
Okay.
And half the one at x equals 0 across, and then half the one at y equals 0 up.
Okay.
I think you could probably do that.
Fa-
Kind of like diagonal.
Okay, so your idea is I can move this up, that's 1 move, 2 moves, 3 moves.
Yeah.
So that would work. We can do it in 2 moves. Anybody see how to do it in 2 moves?
The one is 0 to the left,
Okay, the one at 0 to the left over here.
or like the second one to the right.
This one?
Yeah.
Yes.
Hop that over.
Hop this one over 1
And then up.
and up 2. So we can get up to the line y equals 2. We're killing a couple of checker pieces, but we have infinitely many. small losses will be acceptable. All right, so we're all happy that we can get up to 2. Can we get up to 3?
I think so.
All right, so how could we get up to 3?
So once we get up to 2, now we have 1 at 2.
All right, so how do we want to get up to 2? Do we want to get up to 2 with a 2-way?
Yeah.
Or?
That's a good way.
All right, so wait, so we've now gone. All right, so we've hopped to here, boom, boom.
Then we can push to the one on like x equals -2. So kind of like the same side.
Okay, x equals -2?
Yeah.
All right, so move this one over to here.
Right. And then somehow fill the space below it. You have many options.
Well, no, I think we're in really good shape right now.
Right. And then you can either from the left or from the bottom fill this space at y equals -1, and then you can hop up twice and you get to y equals.
Yeah, I mean, we could just take this piece over here and go boom, boom, boom. Or we could go boom, boom, boom.
Yeah.
So So what do you think the conjecture is?
You can get infinitely far up.
Anybody have any idea why I drew the line at y equals 5? Can't get up to y equals 5. You cannot get up to y equals 5 with finitely many moves. It feels like you should be able to do this. This is the fun thing about teaching a class like this. We can take the time and we can ponder this, we can go slow. I mean, it seems like I've got so many pieces, I can just slowly start migrating things upward. There's gotta be a way to do this.
Every time that you make a move, you cut your number in half.
Which number?
Well, every time you make a move, you turn 2 pieces into 1 piece. So
Yeah, but I've got infinitely many pieces. This is Princeton.
So if you migrate them up, you're going to constantly thin out the number of pieces. And then if you try and shift some over,
Okay, so have we done the Hilbert Hotel in this class?
that's the infinite rate
Right. Do you guys know the Hilbert Hotel?
in this class. But
It's always full, but there's always room for one more. How many of you have not seen the Hilbert Hotel? So you have a hotel with infinitely many rooms, and then somebody arrives and they want a room. And they have a lot of money. So one thing you could do, of course, is you could just kick someone out of their room. But this is, you don't want to be a cruel manager. You don't want to get a reputation of kicking out people. So Hilbert Hotel. So we have infinitely many rooms. 1, 2, 3, all full. And then someone arrives. So how do we allow this? If you've seen this before, don't say anything. How do we take into the hotel the new guest without having anybody lose a room? Without throwing anybody on the street. Let's phrase it like that. What could we do? So how many of you have not seen the Hilbert Hotel before? Have you seen the Hilbert Hotel? Okay. Has everyone seen the Hilbert Hotel? Okay. So if everyone's seen the Hilbert Hotel, then there's no one who hasn't seen it who can answer the question. So what you would do is you send your person in room 1 to room 2, the person in room 2 to room 3, the person in room 3 to room 4, and so on and so on and so on. And this now frees up room 1 for the new person. You could even have infinitely many people arrive. And if you have infinitely many people arrive, you send person 1 to room 2, you send person 2 to room 4, you send person 3 to room 6, you send person 4 to room 8. And if you do it like that, you've now freed up all the odd rooms for infinitely many people to take. So whenever you're working with infinities, you've got to be careful. Even if we lose half of our stuff every single time, we still have infinitely many.
Right. I think it was more of kind of, you might not be able to get a substantially large portion up to y equals 4.
Right,
Every
but
time you get a chunk and try and send it up, it slowly disintegrates.
right, and then the question is, how much is disintegrating near it? But I've got a greater depth down below that hopefully I can just start moving things up.
Right. So I think that it would also be a function of the size of the chunk, right? The larger the chunk, the more moves you have to do, which is the more pieces disappear.
Let's see. I could take this piece here, move it here, and then here. So this piece could go here and then here. So it'll kill this one. It'll kill this one. It's now here. This one I could go here, here, here. So I'd kill that. I'd kill that. And so now I'm really getting set up to get into 4. I want to just put a piece over here. Well, I can do that.
Or you can just take the one at y equals -2 and x equals 2 and send it up to the left. Up.
Okay, y equals -2, x equals 2. Right. So I can set this piece. Good. Boom, 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 boom.
And you're saying that now you cannot get it any higher.
Yeah. At least we got up to 4. Now again, there's probably other ways to get up to 4. And so maybe this is not the best way. So the hardest part is to figure out what monoinvariant should we look at for this problem. And so I'm deliberately not assigning huge amounts of homework problems. I really want to give you the time to just play with some of these problems. That's why I'm giving lots of extra credit problems. And just look at the ones that you find interesting. It is not easy to figure out a monovariant for this problem. Is there any point that looks particularly interesting in this problem? Yeah, which point on the lattice do you think might be the most interesting point? And there are infinitely many points that are equivalent to this, but we can always change our perspective and make this one point particularly nice. So what's our goal? What are we trying to do? Yeah, we're on the line y equals 5. Yeah, we might as well say this is going to be the special point right here. Right? Because without loss of generality, if we're somehow getting to the line y equals 5, we might as well assume we got to the point 0. Now, that may mean we don't stop by moving the piece at x equals 0 or y equals 0, something like that, but well, the problem is the number of checkers below it is infinite.
So that would be a bit hard to...
So you could have it as infinite, but then the monoinvariant would just be identically infinite. So again, we're only allowed finitely many moves. We're not allowed infinitely many moves. If you could do infinitely many moves, would things be different? I mean, you could potentially have the whole thing, this whole row jumps that whole row. Again, I don't know if this would work. But even if you were to do something infinite like this, would you then be able to just throw away all but finitely many? Would we really need infinitely many of them to have it come all the way to y equals 5? Or would just a finite subset of those moves have been enough? My feeling is there's not going to be a solution with infinitely many moves. That if there was something that would, yield it, it would have also yielded it with finitely many. But so somehow we've got a special point here to play with. We've got to come up with a monovariant. But it is not clear what that should be. The number of points, it can't be the number of points.
Could it be the number of empty points?
So it could be the number of empty points. Now, every time you do a move, the number of empty points is going to grow by 1, unless something comes up to one of these rows. So how do you count something up here at y equals 4? Is that counterbalancing empty points?
I mean, I don't know. It just was something that wasn't infinite.
No, and this is what you need to do. And again, I don't particularly care about the solution for this problem. I care about the thought process of how should we attack this problem. This is one of the reasons why we don't have a real textbook for this class. Because I don't want you reading things that we're going to do. This is why this class has such high class participation. Is if you read something, it colors how you look at things. And as professors, we can do this. I don't know if I should be admitted this on exams. Depending on how we write the exam questions, we can get you to think about trying certain ways. When the camera's not rolling, I might tell you about some things I did when I was at Brown. But over here, what do we want? It's got to be something that's not infinite. Or maybe it's something that's infinite, but they're weighted. We have infinitely many objects. If everything has the same weight,
So I would say like 1/2 and then a quarter and then an eighth.
so maybe there's a different weight on each piece.
Oh, so like weight each piece as like 2 to the like row level.
Okay,
Prove that.
so you're looking at something, you're doing something right and something wrong at the same time, so they almost balance.
Well, if you look at each piece, it's infinitely many wide.
Right?
You can't look at
So somehow we're going to need things to be, we're going to need to somehow get something that converges. When we solved the Fibonacci's, we used what method first? Anybody remember how we first solved the Fibonacci's?
like it solves for the general formula.
Yeah, how do we get Binet's formula? We solved the recurrence, but how do we solve the recurrence? I'm sorry? No, generating functions was later. We had the method of divine inspiration, right? So a very powerful way to solve these problems, right? So I strongly urge you to become divinely inspired. Right now. It would be a great moment for it. All right, does anybody feel divinely, I'm not sure if I'm allowed to ask that question. Okay. This method is a little fickle, okay? You cannot always count on divine inspiration. But let's think about what we did at Fibonacci's. How did we do the divine inspiration?
You know that I just kind of the way that I did it, I never really did the divine inspiration with like the 2-term formula.
Right.
But I think when I was younger, I kind of said, what if it had a constant rate? What would that rate be?
Mm-hmm.
And then you can solve for r such that, r squared equals r plus.
Right, so we guessed,
So you can guess that the major
right,
term
Fn was r to the n. And then we saw that if there were 2 different roots, we could get Fn would be, c1 r1 to the n plus c2 r2 to the n. But the way we guessed was we gave ourselves a free parameter. Right? I did not say, you know what? I think Fn is 1 over root 5, 1 plus root 5 over 2 to the n minus 1 over root 5, 1 minus root 5 over 2. Yes, that looks right. I mean, this is really divinely inspired. I mean, at this point, people are worshiping me as a conduit, right? I could have written this down. If I write this down, can you prove that this satisfies the Fibonacci recurrence? How would you do it? Induction. When n equals 0, we'll get, 1 over root 5 minus 1 over root 5, so good. So f of 0 is 0. F of 1, all right, so the 1/2s cancel. The root 5 over 2 reinforces and becomes root 5, which cancels the root 5, and we get f1 equals 1. And now we do induction. So the way to prove Benet's formula is to write down Benet's formula and show it works by induction. This is possible, but it's much, much harder. And then in a whole class of problems, if I tweak things a little bit, if I say fn plus fn minus 1 plus fn minus 2, then you would have to figure out how it changes. The better way is to say fn equals r to the n, and I have a free parameter r. And then I see what choice of that parameter will work for the problem. So let's go back to what we're doing over here with the Conway problem. If we try to solve this directly, your idea was to put in a 2 or 1/2, 1/4, 1/8. So this is why I said you were partly good and partly bad. You were good in that you were giving yourself some kind of parameter that's going to give you some type of convergence. But you were bad in that you were saying ahead of time what it had to be.
So you just give it as a number less than 1.
Yeah, probably some number less than 1. Now, I will admit I have prepared this problem a little bit, and so I know what the answer is. I think it's absolutely amazing that the answer is somewhat related to the Fibonacci's. Well, if ours is the golden ratio, we could have trouble with convergence, but maybe 1 over r. Just interesting to just see how the semester can tie together. So we would want some way of assigning values to quantities. And then what we would want to do is, you give me a board configuration. I'm going to attach a weight to every piece. And that will give me a value of the board. And then I do my move. And when I do my move, that changes the value of the board, but it's going to change the value of the board in only one way.
It's going to only go down.
It's either going to only go down or stay the same. So again, right now we're just trying to find out structurally what might the answer look like. So we want to somehow add weights. Yes. Probably less than 1. And we want convergence. And then somehow we want it to be a monovariant as we move. So whenever I do a horizontal move or a vertical move, the value of the board can't go up. And finally, the value with a piece at 0, 5, and somewhere else exceeds the initial configuration.
So is the value at, is the way that they proved that you can't do it with a finitely amount of moves, was that they proved that the value at 0, 5 was equivalent to the maximum value?
So the way it works is that if you have a piece that's 0, 5, you've got to have one other piece somewhere else on the board because we have infinitely many pieces.
Right. So if there are infinitely many moves, that might not be the case.
That might not be the case.
Okay.
And so somehow, if we have a piece at y equals 0, 5, I think that might have the same value as the initial configuration of the board.
Okay.
And then since there's got to be at least one other piece somewhere else, so a weight 0 less than the weight, which would be a function of your xy coordinate, which would be less than 1. So this at least gives us a framework for trying to think. So we want to somehow assign weights to each piece. And somehow if a piece is over here, it's going to have the same weight as the entire initial board.
But if the pieces, so we have to weight the x coordinate as well as the y coordinate.
Right, because we need things to converge. So you could have maybe a different weight for each row, and then within each row, maybe you have an additional weight as you move downward. So
Maybe like this number less than 1 raised to the like row number plus column number.
yeah, so maybe somehow the weight is going to be related to your row and your column number.
I think that might work. And then I think that if you can kind of go back to the Fibonacci's, as long as you say that,
So now I just want to be careful. So y is going to be negative, so that's good. So it'll be row to the j, and then maybe row to the absolute value, to the negative absolute value of I,
yeah. in
something
this
like that.
case- Yeah. In this case, you would want your weight to be greater than 1.
Right, so if we're writing it like this, then we would want row to be greater than 1.
I think that if we say that that hopping a piece is equivalent, if we say that hopping a piece, your end state is equivalent to your previous state, that would be, r to the 2, like r squared equals r plus 1.
Okay, so
So
you're talking about like a horizontal hop?
or a vertical hop, either way, right? If we go from, we have 1 at y 1 and 1 at y equals 0, and we go to y equals 2, we ended at row squared, and we started at row plus 1. If we
But
did that,
maybe we want the vertical moves to, I don't, maybe these are not the same rows.
that's possible. But I think
So,
that if we,
you might want some extra freedom. Row vertical, row horizontal.
right, but I think we have to say that row is going to be greater.
Yeah, but the way I'm writing it right now, it would be greater than 1 because this is going to be a negative number.
Right.
And then as you start coming higher, you're going to start getting more and more credit.
But not just greater than 1. I think it would have to be greater than the golden ratio.
So,
Because the golden ratio fulfills, if, let's say we start at, y equals 0, x equals, we start at 0,
So-
0, and 0, 1, and then we end at 0, 2.
well, so what we can begin to see is we can begin to see the connection with the Fibonacci's. That when we're somehow doing these moves, we really are combining two adjacent pieces and getting the next one. And so we want to choose a set of rules so that horizontal and vertical, at least one of them is lowering the value of the system, or maybe both are, but maybe at least one is. And so somehow if we were to get the new value is going to be too much. It might be a little bit better to give us a little bit extra freedom. Why do we want to use weights like this? We know how to sum a geometric series. And so again, this is not a solution. This was a guided thought process as to how we might attack a really challenging problem like this and come up with a monovariant, because nothing is screaming at us what it should be. We've got infinitely many points. How do we deal with infinitely many points? We put weights on them, so that the further away you are, the less you count. Right? This doesn't mean the people who are watching this remotely from Swarthmore and Amherst don't count. We like you. We just don't like you as much as the Williams students who are here. But the weight is really close to 1. Okay? So for something like this, this is a good thought process, but this does not solve the problem. So I'm not going to assign this. You don't have to do this for Monday, but I strongly urge you to try to see if you can write up a solution to this. Now, of course, with something like Google, Conway's famous checker problem, it's probably not that hard to Google this. right? This is the danger of telling you what the problem is named. But this is not the point of this class. It's, challenge yourself a little bit. Have some fun. Enjoy the weekend.